In the last module, we started talking about how to model heat sinks using heat exchanger theory, and we continue on that in this module. And as we talked about, we use the counterflow heat sink or counterflow heat exchanger theory as a way to model the heat sinks, and where we see is that the solid walls will be treated as one stream versus the air stream to be treated as a second stream, that is, and the solid wall will be treated as a heat sink or a fluid stream where it is almost isothermal. So it is maintained at some hot temperature, that is the solid wall, because it is in contact with the heat source, we treat that as a hot side stream, and it is maintained at some hot temperature, T hot, while the cold stream is the one that undergoes a lot of sensible heat rise from cold in and picks up the heat from the hot stream and becomes cold out. The best case scenario for the heat sink design would be to see that the hot side temperature is imprinted on the cold side temperature outlet, that is, T cold out should be equal to T hot in to achieve effectiveness of that heat exchanger to be on the order of 1. So in this formulation, if we treat, because as we talked about, the solid side heat sink part will be treated as if they were undergoing phase change. That means the conductance of that caloric conductance of the hot side is going to be quite high. So air side caloric conductance is always going to be the C min that we are typically after. So the cold side stream will be the C min in this case. Then we can write the effectiveness of this heat sink. If we write it based on the numerator based on the air side, which is T cold out minus T cold in divided by the C min, and the numerator is also air side caloric conductance, so they get cancelled out. So you have the denominator as T hot in minus T cold out, T cold in. So the T hot in is nothing but T base for a heat sink, and T cold in is nothing but air side inlet temperature for the heat sink. T cold out is the air side outlet temperature, mean temperature of the heat sink, minus the cold inlet temperature, that is the T temperature, air inlet temperature of the heat sink. So describing actual heat transfer as effectiveness, if epsilon times C min times T hot minus T cold in. So this is a better way of describing them. Then using this idea, then one can write based on the discussion that NTU is nothing but typically overall heat transfer coefficient times area divided by C min, and we can use this definition of NTU to describe our effectiveness as 1 minus exponential of minus NTU. This is coming straight out of the heat exchanger theory. We're not doing anything else except that the NTU is now defined based on HA effective, which is the heat transfer coefficient for the fins. A is the effective surface area of the fins divided by the mCp of the air, which is m is the mass flow rate, Cp is the specific heat capacity of air. So this gives us the NTU relationship for this is coming from the counterflow heat exchanger theory. So then Q actual is equal to m dot Cp times effectiveness. T hot in now is T base, temperature of the base temperature of the heat sink, minus the T air inlet is the T cold in, and this, if we write it in terms of NTU, is nothing but mCp 1 minus exponential of minus NTU times T base minus T air in. So if I want to write a resistance, then it is nothing but T base in minus T air in divided by Q actual will fetch me 1 divided by mCp times effectiveness, which is nothing but 1 minus exponential of minus NTU. So this exponential can be expanded using the so-called power series. Exponential of minus NTU will give me can be written as 1 plus 1 minus, because minus NTU, 1 if it is exponential of minus x can be written as 1 minus x plus and so on. There are many number of terms. If we just use the first two terms, we get that 1 minus of 1 minus x will fetch me this entire bracket will drop off and all you will have is MCP times NTU. That is, what this does is that one gets MCP times NTU, which is nothing but HA effective divided by MCP. So HA effective will only remain. So in when you linearize it, when the linearized form is acceptable, that is when the fins are faced large apart, then one obtains this the so-called convective heat transfer model that works well. Otherwise, a typical resistance model should always be described based on the thermal resistance of a heat sink is always written as 1 by m dot C sub P times the effectiveness in the denominator, the product of mass flow rate, specific heat, capacity of air times the effectiveness, and the effectiveness is nothing but effectiveness is equal to 1 minus exponentially of minus NTU. NTU is the number of transfer units. So with that, we conclude the heatsink modeling exercise that we have undertaken. The practical considerations are a lot more, and we will briefly discuss the practical side of how to design these things, because it involves, when you are talking about an active heatsink situation, it involves a lot of factors, and one main factor is how to choose a fan. There are a number of varieties of fans that are available, but typically in an electronic setting, often one uses what is called the axial fans, but there can be centrifugal fans, a combination of these two things, so-called special designs, and there are so-called tube axial fans, and you see these are commonly used in The centrifugal fans are often used when you have an inlet placed at some location, in a laptop. Typically you see a inlet centrifugal fan, because inlet for the air is on the bottom surface and the air is turned almost a certain angle and it is blown across the heatsink close to the vent. So then the servers and desktops typically see axial fans, and if you look at a fan curve that is typically used, there are two parts to it. One is the so-called fan curve itself, the static pressure. What you're seeing in this figure or slide is that you have static pressure on the vertical axis versus airflow rate. CFM is cubic feet per minute. This is, even though this is not a SI system, many suppliers provide information only in terms of this millimeter of water or inch of water as a pressure drop and cubic feet per minute of airflow rate, which is nothing but a volumetric flow rate. If you convert it into SI units, it is cubic meter per second. So this is often the fan curve that is specified in many vendors' catalogs. Is that you have what is shown here is the fan characteristic curve for a given RPM, that is the rotations per minute. If for a specific RPM, as you increase the RPM, this curve shifts top like this. So, and then because air is flowing through the heatsink, it incurs, for a given flow rate, it incurs certain amount of flow rate. It incurs certain amount of pressure drop. That pressure drop is described in this line. So that is what is shown here. For a given pressure flow rate, there is a certain pressure drop across that heatsink, or as an example, and that is often described by this curve, and where it intercepts with this so-called fan curve is the operating point of a heatsink. So a fan curve can be thought of in two ways. One is, many fans always provide what is called maximum pressure drop versus maximum flow rate. So you get, for a given fan, you obtain maximum flow rate when the pressure drop, the back pressure is 0. That is, this is the maximum flow rate obtainable for a given fan design, versus when you have 0 flow, then you obtain the maximum pressure drop that it can undertake. So these 2 points are, in many fans, are specified only these 2 points, and sometimes it is very simple to just extrapolate it instead of getting this curve and just draw a linear line, and this is to be obtained either numerically, experimentally for a given heatsink design, and you look for the intercepting point, and that is the point of operating, operating point of your fan system. And typically there are regions where you get what is called stalls in the fans and you don't operate in those regions. For example, in this case you have a curve, the fan curve comes and it flattens out. If I were to look for a pressure drop of, let's say, something like this, then I can have multiple flow rates. That is, I can have Q1, Q2 and so on. So typically one avoids operating in this region, and always a fan is operated beyond this so-called flat curve and without getting into it. The other aspects of fan selection is how much volume flow rate is needed, what is the fan static pressure that these are the two parameters that we discussed. But then what is the environment that it is in? For example, is it dust, noise specification, because the fans always have they generate lot of noise in their systems. The fan noise generated is quite high, and in some occasions, and one has to, because of noise requirements stipulated by some regulation authorities, one cannot select a certain fan even though it may deliver flow rate and pressure drop that you require, but if the fan noise is so high that one has to not select such a fan. So noise becomes and noise has certain things called blade passing frequencies. If the heat sink is close to that blade of the fan, then certain harmonics that are created. So those also need to be looked into, because the fan noise at lower RPM may be fine, but at higher RPM they may start to have squealing sounds due to these tonal sounds from the fan's blade passing frequency. And then the operating temperature, can the fan withstand higher temperatures? So operating temperatures and the type of implementation, whether can an axial fan work or a centrifugal fan work, and so many parameters. And for example, what is shown here, this is an image caught from Wikipedia, and you can see that in Indian subcontinent, typically we see that when you open a laptop, there's a lot of dust that gets agglomerated, collected at these fans, because fans are heat sinks, because they act like filters and they collect these ducts. And so one has to be very careful in such situation how to choose a fan for in Indian subcontinent and so on. So the fan laws, we won't go into the details of fan laws, but instead we'll just describe them, that if you are just interested in scaling up from a given fan without changing any other thing, if it is a 80 millimeter fan and you want to go to 120 millimeter fan, or you want to understand the effect of 120 millimeter fan, then using these fan laws, typically one can easily obtain what could be the flow rate, power, pressure, back pressure and so on. So the fan laws are quite useful in such situations. And Q2 is the new fan design that you are interested, that is the flow rate here, volumetric flow rate that we are talking about. Q1 is the current fan flow rate, volumetric flow rate. Size of the fan of the newer size that you are interested in, say for example from 80 millimeter fan to 120 millimeter fan. So that is cubic dependence. And then what is the RPM, if you are interested in going to higher RPM or not, it could be 1. So the change could be in RPM, in size, so you obtain certain flow rates and pressure drop. Similarly, this P2 is the back pressure that the fan can withstand for the new fan. So similarly, the expressions are given. Rho is the density of the air if it is going to be operated in a different fluid other than air or something like that. So one can use these fan laws to our advantage in designing these heat sinks, let's say higher heat sinks, higher flow rates and so on, or smaller heat sinks and smaller flow rates using these fan laws. So with that, we'll just move on, and there are many ways to optimize these heat sinks. And as we talked about previously, that could be fixed mass flow. I have a heat sink, I want to optimize it. I want to optimize in the sense the optimization exercise often involve I want to dissipate as high a heat transfer rate for a given pressure drop or given parameter, or I can, keeping the same heat transfer performance, I want to minimize my power consumed by my fan. So there are many ways to look into it. In our case, what we are going to look at is these parallel plate fin heat sinks. How can we improve, given the volume of the heat sink to be same, how can I improve its performance? And this involves, can I fix my mass flow rate? How do I improve this? Is that, can I fix my mass flow rate? Can I fix my pressure drop? Can I fix my pumping power? Can I use a prescribed fan curve? So these are the possible methods, but if I keep my fixed mass flow rate, then there is really, I don't control the pressure drop, then there is no really a minimum, the resistance can go as low as feasible, because I can keep adding the area of the fin or so on and so forth. So there is typically no clear optimization that can be obtained with the fixed mass flow rate case, but in the case where you have a lot of flow bypass, a fixed pressure drop is a good constraint to keep and try to optimize your heat sinks. Or you can keep fixed pumping power, which is very good as an energy metric, and the third one or the fourth one is typically the fan curve that we just talked about. So we'll just use the pressure drop metric as a way and deal with what is a quick make a quick estimate, and this is obtained theoretically by Professor Bejan and Chiuba in a classical paper in 1992, and what they do is develop an order of magnitude estimate of how to design these, optimally place the fins in a heat sink. So what you are seeing here is that there are these blue lines of the fins and the volume is fixed. This is a top view. The width of the total width of the heat sink is kept at h. The flow comes in at some T inlet or T infinity and flows along the length of the parallel plate of L, and there is some certain depth as well that is not discussed here. And the flow is considered to be hydrodynamically as well as thermally developing as well. So it doesn't restrict itself to some developing flows. So what they did into obtaining optimal spacing is that the interesting result they obtained is that if you calculate thermally developing length, that is typically the length one should use, is what they obtained as a result, and we'll see how they obtained it in the next couple of slides. In the figure shown, as I talked about, the fin stack width or the heat sink width is h. Fin thickness, this thickness is maintained to some thickness T. Spacing between the fins is defined by this D, which is the hydraulic diameter, or spacing between the fins could be treated as such as if you are talking about purely a parallel plate construction, and the fin temperature is assumed to be T wall. This wall is maintained at isothermal temperature T wall. When one obtains an isothermal temperature when the fin efficiencies are close to 100%. So assuming that the fin efficiencies can be maintained at very high level, this assumption of constant wall temperature is quite good. And so if the thickness of the fin is much smaller than the spacing between the fins, which is often the case in electronics these days with those zipper fins, the thickness of the fins are close to 0.2 millimeters, and the spacing between the fins could be on the order of 2 millimeters or even higher in some cases, then we can say that the n number of fins without accounting for the thickness of the fin is equal to h divided by the d, and the length, as we talked about, is the flow length is about capital L here. So they looked at it as two possible scenarios. One is the so-called fully developed flow limit. The spacing between the fins is so small that the flow develops to a fully developed flow very quickly in a very short length. That is, this length is 1% of the total length. So the flow becomes quickly fully developed flow. Then what they obtained is called the d tending to 0 limit. And then using the Poiseuille flow that you may have discussed in previous modules, the velocity going through these fins for a fixed pressure drop, that is their constraint, is the spacing between the fins, d square divided by 12 times mu is the dynamic viscosity and L is the length. and from this velocity one can obtain mass flow rate per unit depth into the page, and you have rho u h. We are treating the unit depth in the sense the depth of the fin going into the page as some sort of 1 meter, even though you can relax that assumption, this is for simplicity. So then rho times h, we use the u expression from the Pascal flow approximation. From this, using mCp delta T, then one can write the heat transfer rate per unit length as this. This is the fully developed flow limit when d tending to 0. On the other hand, this is the case when the fins are so far apart. The previous case talks about fins being placed so close to each other that they develop, that is, fin density is quite high. On the other hand, the fins are placed so far apart that the boundary layers that are not interacting at all. The first boundary layer from the first fin is not in communication with the second fin, that is, the gap between the two fins, the boundary layers, the thermal boundary layers are not even in contact. So these are two extremes that we are interested, and if you notice that using Blasius solution that one can easily obtain a relationship of this form, and that is what is given. This is just purely based on Blasius solution using heat transfer coefficient from Blasius and writing that into a total heat transfer rate, and one sees that the heat transfer rate for this case is inversely proportional to the spacing between the fins raised to the power 2/3. On the other hand, for the d tending to 0 limit, the heat transfer rate is increasing as a d square. In one case, heat transfer rate is inversely proportional to d. On the other limit, the heat transfer is increasing is proportional to d square. So there is a crossover of these two situations, which are two asymptotic or two limiting cases. So when they plotted it, this is the so-called, what you are seeing here is that this dashed line is the d raised to the power -2/3, that is the inverse part of the limit, which is the limit number b, which is d tending to infinity limit, and the first limit says that heat transfer rate is proportional to d square, and what is plotted on this graph is the heat transfer rate as a function of d, the spacing, and you can see that they intersect at some point, and this point happens to be the optimal spacing. This optimal spacing between the fins can be obtained by taking this expression for d tending to infinity and d tending to 0 and equating them, and one obtains, because at this cross section point is where the optima exists, is what their theory is, and it turned out to be, from experiments and numerical models, it turned out to be quite true, and so they obtained that. So you can obtain this optimal spacing between the fins by equating the two limits, and that is what is given, and this optima, at this optima you obtain what is called the maximum heat transfer possible, and this is given by this expression. And they also showed that by thorough analysis, very detailed analysis, as well as we have done some experiments and some other groups have done experiments on these things and showed that this is actually turns out to be quite close to the optima that one obtains experimentally as well. And the main conclusion that arises from this discussion is that the spacing between the fins should be done in such a way that the length of your heat sink should be equal to the thermal development length. The reason being is that if you allow the boundary layers to merge very quickly, then once the boundary layers merge, the heat carrying capacity of air is quite reduced. On the other hand, if they don't merge at all, then you are not utilizing all the cold fluid temperature that is going through. For example, in this case, there is a cold temperature, this is the thermal boundary layer, and as it exits, the cold temperature stays cold, so it is not completely utilized. In this case, the cold temperature is completely overutilized, so a best case scenario will be that this boundary layer merges with this boundary layer at some point close to the exit, and that is what they found out, is that the spacing between the fins should be such that the flow becomes thermally fully developed at its exit or closer to its exit. And this is typically a very good rule of thumb when you are trying to do longitudinal heat sinks. And so there are many similar, this method is called method of matched asymptotes, because we are talking about two asymptotic behavior, d tending to 0 behavior and d tending to infinity behavior, and we are matching them at wherever they are crossing over, and that turns out to be a very good way of estimating. And as we discussed, that you want to keep your d, the spacing between the fins, to be in such a way that at the length, at the volume constraint, that is the length of the heat sink, should be where the boundary layers merge. And those boundary layer thermal development length are well documented in many books, and I am sure you may have had some modules where they talked about thermal development length. So using those principles, one can easily design a very initial good heat sink design can be obtained by using such a guideline. With that, we end this module.